now it's time to think about the dimension of self-similar fractals. And before we do that, let's remind ourselves of some other dimension ideas. So I've just drawn a few objects that all have dimension 1, and that's because we could parameterize the points on each of these curves using just a single number. So these are 1D objects. And then let me sketch some 2D objects. And perhaps you can see that it takes 2 numbers to parameterize a position on this surface. And so surfaces are 2-dimensional objects, and solids, we need 3 numbers to describe where we are in the solid. This is my attempt to draw a solid sphere. Really didn't go very well. But we need 3 numbers to parameterize a point on the solid. And off the top of your head, you probably know 3 different standard coordinate systems for parameterizing in 3D. That would be spherical and cylindrical and rectangular. But of course, one could generate other methods of parameterization. Anyway, these are objects that we've been encountering at least since multivariable calculus, and that we're relatively familiar with attempts to parameterize, and thus with their dimension, because we need 2 parameters, 1 parameter, 3 parameters. What about the Cantor set or other fractals? How does our notion of dimension translate to those? Let's consider an example that's not the Cantor set, but also starts from a line S0 and involves keeping the edge thirds, pretend those are thirds. But now, instead of just dropping the middle, let's replace it with the other 2 sides of an equilateral triangle. So we dropped this bottom side and added in these 2 sides. And then let's do that again. In our next step, so this will be S1, in our next step, for every line segment that we have, and these are all equal length, they're just drawn badly, we're going to replace the middle segment with 2 pieces of an equilateral triangle. And imagine continuing this process. So what we're seeing is a type of snowflake growing from what we started with, which was a line. And then these get little bits. Oh, this is very hard to draw. So imagine this curve continuing to get more and more complicated as we approach the von Koch curve. And then we can ask, what's the dimension of this curve? Well, I'm calling it a curve, so maybe it's a 1D object, but actually, okay, S0 has length 1, but S1 has length, 1/3, 2/3, 4/3, and S2, okay, this length was 1/3, but with these 2 pieces it became 4/9, so 4/9, 8/9, 12/9, 16/9. Okay, so we went from a length of 1 to a length of 4/3 to a length of 16/9. Perhaps you're seeing that at each step of the process as we try to create the curve, actually the snowflake curve is getting longer, and so in the limit, our length is not going to be bounded, and because this curve has an unbounded length, we're not going to be able to parameterize it. We can't parameterize this as a 1D object, and that might intuitively make sense, because if you zoom in on a little piece of it, and zoom in, and zoom in, and zoom in, you're never going to get a straight line. No matter how much you zoom in, you're going to keep seeing this same spiky, snowflakey structure. So intuitively, I guess it shouldn't be 1-dimensional, but at the same time, it's definitely not 2-dimensional. There's no area that seems to really be getting covered, and so we expect it to have a dimension in between 1 and 2, and we need to find some way to define that notion. we're going to define a simple way of thinking about dimension that's going to be called similarity dimension. This definition is going to take advantage of the fact that the simple fractals we're thinking about right now are all self-similar. And that means that if we take a small subset and scale it up, it looks like the whole fractal. Or if we take the whole fractal and scale it down, it looks like a small subset of itself. To think about similarity dimension, I'm just going to start with an example of a line, and I've put black dots at the end for us to keep track of it. And I want to scale this line down by 2 and ask how many copies of itself we need to reconstruct the line. And when I scale it down by 2, I need 2 copies. If I were to scale it down by 3, I need 3 copies. And etc. If I scale it down by n, I need n copies. Okay, so scale down by n and use n copies to reconstruct the line. Now, what if we were working with a square instead of a line? I'm going to scale it down by a factor of 2. How many copies do I need? It's no longer 2. I now need 4 copies. And then what if I scale it down by a factor of 3? I actually now need 9 copies. So here I am scaling down by n and needing n squared copies. Okay, for a line, I scaled down by n and needed n copies. And for a plane, I needed to scale down, if I scaled down by n, I needed n squared copies. So perhaps you can see that the number of copies I'm needing is scaling with the dimension. If I used a cube and scaled down by n, I would actually need n cubed copies to reconstruct the original object. These exponents are a reflection of the dimension of the object. To state this explicitly, the similarity dimension is given if we scale down by a factor of r and then need to use m copies. The number of copies is equal to the scaling factor raised to the dimension. So for the 2 examples we looked at a moment ago, the line, we had the number of copies that we needed equal to our scale, m equals r, and this implies that d equals 1. And for the plane, we had m equals r squared, which implies d equals 2. This is just as we expect. The dimension of the line should be 1, and the dimension of the square should be 2. For the Cantor set, we're scaling down by a factor of 3. So scale equals 3, but copies is just 2. We scale this piece down by a factor of 3, we copy it once, and we copy it a second time. And so we have 2 copies equals our scaling factor to the d, and solving for d, we take the natural log of both sides, and we get the natural log of 2 is equal to d times the natural log of 3. So we solve for d, and we find that it's the ratio of the natural log of 3 to the natural log of 2. And if we take that ratio, it's about 0.63. So this is not a one-dimensional object, but it does have some dimension by this notion of dimension. Now let's consider, for example, the von Koch curve. Our original object gets scaled by 1/3 and then copied 4 times. So the dimension is given by the need for 4 copies is equal to 3 to the d. So solving for d, we find d is the natural log of 4 over the natural log of 3, and that's actually about 1.26. And so this is, as we had said, the dimension is more than 1, but it's definitely not so close to 2 because we're not really space or area filling. We described one kind of Cantor set earlier, but you could imagine choosing a different scale and a different number of copies. So this is an example where we've chosen to scale down by 5 and make 3 copies. This is called the even fifths Cantor set. Of course, there's a whole family of Cantor sets. that could be made by taking different scalings and different number of copies. So scale 5, copies 3. Let's find the dimension for this set. So 3 copies equals 5 raised to our dimension. Our dimension is the natural log of 3 over the natural log of 5, and that's about 0.68. So that implies that this Cantor set fills a little bit more towards a line than our previous Cantor set, 0.68 versus 0.63. And you could imagine making a Cantor set maybe where you split the line into, I don't know, 11ths, and you take the even 11ths, and that would be even a little bit more space filling. So you could think about the implications of generalizing this, and we could even look at the range of possible dimensions that we're able to get with these kinds of every other Cantor sets. This speaks to a more general notion of a Cantor set, and so we're just going to write down 2 properties that make up the properties of a topological Cantor set. Topological. The first is that the set needs to be totally disconnected. For these sets that are being made on the real line, what we mean by that is that the set contains no intervals of the line. The second property used to define these topological Cantor sets is that there are no isolated points in the set. Any point has an arbitrarily close neighbor to it. If we think about the Cantor set that we started practicing with, if you're looking for a neighbor within 1/3, you know that every point that lives in this part of the Cantor set has a neighbor within 1/3. And if you're looking for a neighbor within 1/9 and your point is in this part, you know that there's a whole bunch of points that live within 1/9. And of course, for any arbitrarily close distance you choose, I can find a little line segment that I know has an uncountable number of points in it that is self-similar to the whole set, and where all of the points are within whatever distance. And that's because our Cantor set, as we move through these successive lines, length 1, length 1/3, length 1/9, length 1/27th, of course we can get to some s on our way to making the full set where the lines are of arbitrary short length. So that is a generalized notion of the Cantor set.